Okay, well, thanks a lot to the organizers for inviting me to give a talk and for organizing this very vibrant conference. I've been having a great time. Okay, so this is joint work with Chi-Fang Chen, Tropp, Ramon van Handel. We have written 2 papers. So the second one is a subset of us. But this is today I'm going to continue building on what Anthony said. So this is like a new technique for proving strong convergence. And the main result I'm going to give talk about today is in the second paper, but a lot of the techniques are already present in the first paper. Okay, so just as a reminder, there's this notion of star convergence in star distribution, right? Which just means that expected traces of non-commutative polynomials in your sequence of random matrices converge to the corresponding statistic in the C star probability space, right? So this is some finite matrices, and they're converging in some sense to some family of operators. And there's this other notion of convergence, which is stronger. So this is called strong convergence, where so we say that x1n up to xrn converge strongly to a tuple of operators x1 up to xr. If for any non-commutative polynomial p, we have that the norm of this thing converges in probability to the corresponding norm of the polynomial applied to the limiting operators. Okay? So for example, in 91, Voiculescu proved this for GUEs converging to semicirculars, but it's much harder to prove this statement for such models. That was done only later in 2002 by Hagerup and Thorbjørnsen. Okay? And today's talk will focus on proving statements of this sort. And our technique is somehow a method that takes this as an input, weak convergence, which is very qualitative, and turns it into strong convergence.
Jorge, is it literally stronger? Is there a statement that says that if the second true, then the first is also true? Is there a such statement?
That's a good question. I'm not sure.
Is it true that if there is a strong convergence, that there is also weak convergence?
It's
probably
strong convergence to something. You have to say what it converges to.
Right. But Vadim is asking if you have this sort of setting, can you deduce that there's weak convergence?
I think Ramon said it was true.
It's not. I mean, in a lot of the natural examples, it's true. You need to sort of limit C-star algebra to have a unique trace.
Okay. So some people define a strong convergence as having weak convergence plus this sort of non-convergence. But anyways, like if you look at the proofs, you always have to work 10 times as harder for this one than for the other one over there. Okay, so in this talk, I will be working with polynomials with matrix coefficients. So this appeared already in Ramon's mini course. So here I'm going to fix some big D, and then you can think of these non-commutative polynomials as when you evaluate them in non-commutative determinants, basically you can write them as sums of this form. Each term in the sum is a matrix, which is D by D, tensored by a star word in these non-commutative indeterminates. Okay, so Anthony already gave you kind of like some of the ideas of what goes under the hood of our method for some very well-known examples. As per Vadim's request, I'm going to talk about some random matrix model that I believe is out of reach of any of the existing techniques for which we can prove strong convergence. Okay, so what's the random matrix model? It goes as follows. So fix L and V some integers and let K1 up to Kv be subsets. So by this, I just mean the numbers from 1 to L. Okay, so I'm taking V subsets of those. And for each V in V, I'm going to define a random matrix model. So the definition will be as follows. So first, I'm going to take HVN to be an n to the kv times n to the size of kv GUE random matrix. Okay, so these are GUEs, and I'm going to take HVN independent of HUN if V is different than U. So these are GUEs, but they're not necessarily of the same dimension, and they could be large, right? And then what I'm going to do with these GUEs, I'm going to put them all acting in the same space, but kind of like interacting in some funny way. So define GVN to essentially, this is going to be the tensor of HVN tensored with an identity. And I'm going to do it such that this has a total dimension n to the L, right? So I have to take here an L and subtract the dimension of the corresponding GUE. So this is something that belongs, so this is a random matrix, and each realization of this random matrix lives in this space. But importantly, I don't want, so this, because it lives in this space, this is acting on Cn to the tensor L. But importantly, I don't want this guy to be acting always on the same set of tensors, okay? So the copies of Cn on which this guy is going to be acting are going to be determined by the elements in the set of the corresponding KV, okay? So the way I'm going to write this is it is isomorphic. So you look at the copies of Mn that say I in KV, and then you look at the rest. This is I in L, but not in KV, okay? So HV is acting precisely on these copies over here. Okay, is the definition of the random matrix model clear? Yes, Sam?
Is KV an integer?
No, KV, so each of these guys, sorry, so this is big V. And then for each little v in big V, you have subsets of L.
Are there subsets of L?
Yes. So this is, they're subsets, right? So you should think of this as a tensor. You write it down, L copies. You have a specified subset, and your matrix is acting precisely.
Yeah, I see.
Okay? So this is some model that appears naturally in quantum mechanics, in quantum many-body problems. It also appears in random geometries and in relation with some Coxeter groups, and it also appears in operator algebras. Okay.
So Jorge, when you
Yes.
write like H tensor with identity, you mean that it kind of acts in some coordinates it acts at H, and on other it acts as identical matrix.
Exactly. So actually, to help you visualize how these matrices interact with each other, let's associate a graph to this. So let gamma be a graph whose vertex set is precisely V. So remember, this is kind of like the index set for the random matrices. So for each vertex in this graph, we will have a random matrix. And then it has some edges. And here we're connecting U and V by an edge. If KV is disjoint from KU, okay? So if you think about what this random matrix model is doing, this will mean that the non-trivial action of these operators is kind of like happening in different copies of Cn, which means that GB and GUN commute with each other. Okay. So think of the graph, and then think of putting matrices on the vertices of the graph. If you see an edge, then these matrices are kind of like not seeing each other in this interaction. If there's no edge between them, then they're interacting with each other in a non-trivial way. Okay? So the joint distribution or the joint interactions between these matrices is something complicated to describe. And yet, I'm going to try to convince you that we can we're able to get optimal control on the norms of such things. Okay, so there's this theorem of Charles Ward and Collins from 2019, which says that precisely the family of random matrices that I just defined converges in star distribution to a gamma independent family, a semicircular family, S, V, and V. Okay. So if you don't know what gamma independence is, don't worry too much. So this is a generalization of Voiculescu's result, where now because if L was equal to 1, right, then all of these GUEs would be in the same space. And then you're just saying asymptotic freeness to a free semicircular family. In this case, you have a more complicated model, but there's still some way to describe what's happening in the limit. This is called gamma independent. So sometimes this graph gamma, people use epsilon to denote it for some reason. And so people refer to this as epsilon independence. Other papers, lambda independence. And other papers, graph independence, because it comes from the graph product of groups. But anyways, so this is what the theorem says. And the only thing that maybe here I should say is that I'm not going to define what exactly it means to be a gamma independent semicircular family, but note that, or something that it implies, is that if U and V are connected in the graph, then SU and SV are classically independent. And otherwise, then SU and SV are free from each other. Okay?
Jorge, what's the story if each Ki, for example, is the empty set?
Let's not do that. Yeah.
But are there some conditions on the Ki?
Non-empty. Thanks. Okay. So the theorem that we're able to prove is that this family over here, in fact, converges strongly to this family over here. Okay. So I want to tell you a little bit about how one can arrive to a result like this. With no further assumptions. Yeah. So these guys are precisely the ones I've defined over here. Okay.
So maybe one question. So
yes.
People know like what are actually the norms of these things, of polynomials on these things.
I wouldn't expect that to be super explicit. So there's definitely machinery for understanding gamma independence, as you know, right? Like there's this paper of Speicher and Wosiczansky developing cumulants for this sort of independence. There's papers where they use it to prove, to construct von Neumann algebras with certain properties and so on. But yeah, I think this is a complicated relation between these objects, so it's hard to get explicit formulas for these norms. Yes. Okay. So maybe before delving into the proof discussion, let me just give you 2 examples. So one of them, of course, is Hagerup and Torbjörnsen. I think this might be kind of obvious how to get it, but let's just do it for the sake of completeness. So for this, what would we be doing? So you would take L equals to 1, and you can take K1, Kr equals to the singleton R. Okay? So in this case, the graph gamma has R vertices and no edges between them, right? In which case the limiting model is just a bunch of free semicirculars. And this is the theorem of Hagerup and Torbjörnsen. Now, in connection with the Peterson-Thom conjecture, right, you could also take, so let's call this, of course, the highest model. So take L equals to 2, okay? And now what we're going to do is we're going to take K1 up to Kr to be equal to the singleton 1. And then we're going to take Kr plus 1 up to Kr plus S, let's say, to be the singleton 2. Okay? So because L is equal to 2, we have Cn tensor Cn, right? What this is saying is that you have a GUIs independent from each other acting on one of the sides of the tensor. Here you have GUIs independent from the previous ones and independent from each other acting on the other side of the tensor. So this corresponds to some gamma where you have R things over here and S things over here. And then these guys are disjoint from these guys, right? So we have to put a complete bipartite graph between these, right? So in which case, the Peterson-Thom conjecture, so this gives like the n+1 proof of the Peterson-Thom conjecture via a work of Ben. Okay. So maybe before telling you about any actual mathematics, let me tell you something important. So you can think of our method as a machine that turns qualitative statements into quantitative ones. Okay. So for example, the way we prove this theorem over here goes as follows. So as input, we take Voiculescu's result proving that GUI matrices are asymptotically free. So this is a qualitative statement, right? This is some sort of weak convergence. So this goes as an input. It runs through the machine. So we obtain some self-contained proof of Hagerup-Torbjörnsen. Okay? Then we feed this into the machine again. And maybe here we need some concentration, Gaussian concentration or concentration of higher unitaries and so on. Out comes some quantitative version of Hagerup-Torbjörnsen, and importantly, this is with matrix coefficients. Okay, so from here, this is something that Ramon already explained. So if you have exactness, you can, for example, deduce this random matrix statement that implies the Peterson-Thom conjecture. So here, this allows us to obtain the Hayes model. Now we fit this into the machine for some concentration. We're able to obtain some quantitative Hayes. And then, there's some high-dimensional probability argument here, but basically, so here we use the very nice result of Tatiana and Ramon to obtain finally this strong convergence for gamma independence. Just in case it wasn't clear here, maybe I should say strong convergence. We obtain strong convergence for the Hayes model. Okay. So this step over here is analogous to this step over here. So for this talk, I want to focus on this part. Let's say that probably, so some of this was already in Anthony's talk, but I'll make some remarks. But I really want to focus on this part in the remaining part of the talk. And then the other is kind of like analogous, and this is something that already existed. So maybe here is Ilovskaya and Van Handel. Sorry. Okay.
Is there some reason you can't just apply the machine once?
Yes. I hope I can make that clear. Okay, so this is like machine plus. This is the machine from the first paper. Yeah. Okay. Good. So let's see. Let's get to see the machine. Okay, so let's just fix, I'm going to change a little bit the notation from what I had before. So let G1n, GRN be n by n GUE independent GUEs. And S1, SR be free standard semicircles. And let's fix some P non-commutative polynomial with matrix coefficients. And let's find the random matrix. Oh, I don't know why I keep erasing this. Let's define this random matrix over here. So this is a dn times dn random matrix. And then it converges. Well, the limiting object here is going to be, oh, what am I doing? The limiting object over here is going to be a D by D matrix with semicircular entries. Okay. And then we're going to prove that the norm of P of the G's converges in probability to the norm of P of the semicircles. And as Anthony already explained, this is not unique to GUEs. So this works whenever you have this sort of 1 over n expansion. So in the paper, explicitly, we do these cases. We can also do hard unitaries in these groups. and representations of the symmetric group and unitary group. Certain representations. Right? And the point is that, as Anthony was saying, what all of these models have in common is that if h of x is a univariate polynomial, and you compute expected normalized trace of h of your random matrix at level n, then you get a power series expansion in 1 over n, where the coefficients here depend solely on h. Okay? So what I want you to note here is that the left-hand side is linear in h, and from there it's not hard to see that the right-hand side is also linear in h. So note that for every k, the function that sends h to the corresponding coefficient in this series is linear functional on the space of polynomials. So when you run this polynomial method, which uses Markov's inequality that Anthony was explaining, in the case of GUEs, what we're able to prove, but again, if you substitute any of these, you'll get an analogous result, maybe with different parameters. Let's call it theorem 2, GUE case. What we're able to prove is that for every k in C+, no k extends continuously to a compactly supported Schwartz distribution. Right, so initially, for all of these models, this expansion over here only makes sense for polynomials h. Okay?
Okay, can you comment, like, you say that sort of representation of symmetric and unity group, like what kind of representation?
Yeah, so these are the representations that are called stable representations, and they have the property that they're, something being a stable representation actually means you have a sequence of representations which are compatible with each other in some sense. So for the symmetric group, for example, it means you fix a Young diagram, and then you start appending just one box in the last.
Just the long first column?
Exactly, just the column, you just make it grow. Okay?
For unity group, you just add zeros to the signature of representation?
Yeah, so for the unitary group, you have these mu and lambda weights and so on. I think that's a bit more, but there's like an analog version of that. Okay. Right. So note that this only makes sense when h is a polynomial. So what we're saying here is that we can make sense of this for any smooth function, right? So here now you're allowed to input the smooth function. So this is something that Felix's technique can also do in, well, he has worked out explicitly UN and GUE. So this can be extended to a compactly supported distribution. And moreover, for any m, and for any smooth function over here, if you take the expected normalized trace of h of your random matrix, and then you subtract right? So here I'm saying this is equal to some infinite series. Here I'm truncating that series, and I'm about to give you an estimate on the error of this truncation. Here you get, so the rate is going to be n to the m. So here I truncated at time m minus 1. Up here, so there's going to be a constant that depends on h, p, and m. Here is 1 to the n to the m. And then in the GU case, you need an extra term that decays exponentially in n. And yes. So I'm taking xn to be p of the GIs. Yes, yes, yes. And we think of that as being fixed. Okay. And moreover, in the case of GUEs, one can show that only even powers arise, which are going to simplify our argument right now. But this is not a necessity for our technique to work. In the case of GUEs, you have that these distributions are identically 0, meaning that whatever function you input, you just get a 0. Okay, any questions about the technical theorem? So in the remaining time, I want to prove Hagerup-Torbjornsen, and then show you how from there you can get this Peterson-Thom conjecture, and hopefully from there it will be clear how you can go the way up. Okay, So what goes into this, the proof of this theorem, is precisely this technique that Anthony was mentioning. So I'm just going to take it as given, and instead I'm going to show you how to. So let's assume this theorem, and let's prove Hagerup-Torbjornsen. So let's take m to be equal to 2. Okay. So then over here, we're only going to have the 0 term and the first term. And then this is bounded by a constant divided by n squared, right? But then this over here is telling me that this is just 0, right? And something that maybe we should, okay. So now take h to be of this form. So you take the relevant interval over here. This is the norm of the limiting model. I'm going to take an h that's identically 1 in an outside an epsilon blow up of this interval, then goes down to 0, and then goes up to 1. Okay. And note that if over here I take n going to infinity on both sides, well, on this side, only the leading term survives, right? 1 over n to the k goes to 0 as soon as k is greater or equal to 1. So this implies that nu 0 of h is equal to the limit as n goes to infinity of the expected normalized trace of h of xn, right? But by Voiculescu's theorem, we know weak convergence of this. So Voiculescu tells us that this is tau of h of x infinity, okay? Which means that nu 0, so this is true for every h, so this means that nu 0 is the spectral distribution of x infinity. Which means that if I take a function that identically vanishes on the spectrum of this operator, this will also just be 0. Okay. So then if I multiply by nd on both sides, so note that this is a normalized trace and our matrices are dn by dn, I get that the expectation of the non-normalized trace of h of xn is upper bounded by d. So I multiplied by dn, one of those n's will knock out one of these exponents. C. Okay? But then this, what's trace of h of xn? Well, this is the sum of h applied to the eigenvalues of xn. Now this h is 0 if these eigenvalues are inside this limiting conjecture of where alpha and eigenvalues, and it's 1 otherwise. So this is the expected number of outliers in the spectrum, but that's going to 0 as n goes to infinity. Okay? Yes? Oh, so I'm taking these guys to be non-commutative polynomials with d by d matrix coefficients. Okay, so for now, we're just taking it to be fixed. Yeah. So, I mean, this sort of argument was already present in the paper of Hagerup and Tropp. What's new is the input in this sort of form. So Felix also has some version of this, but the d-dependence is different, and that's kind of crucial also for getting what am I about to tell you.
Question.
Yeah.
So if the phi there is independent of the choice of h?
No. This depends on P and H, but this H is fixed for every n, right? Yes. Good.
But in this estimate, h could depend on n.
Yeah, this is true for any n, so this is a non-asymptotic estimate. Good. Other questions? Okay.
Do you have examples where new one is a sports distribution but not a measure?
Yeah, so actually in the case of GOEs, it's a sign measure. Yeah, and once you start going further down this thing, it's not even a sign measure. It has a higher order, so you have to take, even for GOE. So there's a paper of Hagerup and Thorbjørnsen, not the one on strong convergence. There's another paper where they explicitly compute what these are for GOE, I think. Okay, other questions? Good. So, okay, so now I want to show you this sort of bootstrapping argument where you take this as an input, then you use again the machine, and you get, for example, the Peterson-Thom conjecture. So in order to do that, what I want to show right now is that the support of the Kate-Schwarz distribution is contained in here for all k. Okay. So let's proceed by induction. So for k equals 0, we said that nu 0 is the spectral distribution of x infinity. So of course, the support is going to be contained in that interval. So this is true for k equals 0. So let's assume it's true for j equals 0 up to k, and we want to show for k plus 1. Okay. So what we do over here is we invoke this theorem. Okay. Now, okay, so it's going to be important to take h in the form that I outlined there, so it's going to vanish on this interval. So because of the induction hypothesis, actually, and let's take m and take m to be what? K plus 2, so that the last term is the k plus 1 term. Then by induction hypothesis, the first k terms are going to vanish because I know that this is true for the first k terms, and I'm plugging in a function that vanishes identically. So then here I'm only left with k plus 1 of h divided, sorry, this is bounded by this over here, And then here there's a term k plus 1. So then multiply by n on both sides. Sorry, by n to the k plus 1 on both sides. And this becomes an n. And now, crucially, we're going to use that we already know Hagerup-Torbjornsen, and we're going to use that there's a Gaussian concentration for the norm. So by Hagerup-Torbjornsen, xn is almost this. And then by Gaussian concentration, the probability that xn exceeds x infinity plus epsilon decays as exp of c n epsilon squared. But now let's think about what this implies. So this means that it's very rare for eigenvalues to be well outside the spectrum, right? But on the other hand, this function h is 0 everywhere in here. So these two put together you can use to prove, and here maybe I'm skipping like 2 lines, but it's not hard to see that this decays exponentially. Let's say epsilon is fixed, so this has some decay of this sort. But then this term over here has some exponential decay, which will kill any k, any polynomial. So as n goes to infinity, this goes to 0, this goes to 0, which means that this should be 0, right? This is a fixed quantity. Okay. And by the way, so this is something that we realized on our own, but later we found out that Felix has a similar argument. Okay, so it's a bit different, I think, but it's something like this is already present in Felix's work.
Xn is a polynomial, it's not a pure Gaussian, so presumably that complicates the concentration argument.
Well, this constant over here depends on like the Lipschitz constant of P. Yeah. Okay, so maybe to conclude this talk, awesome. To wrap up, let me tell you. Okay, so now we've deduced this. We have Hagerup-Torbjornsen. We've deduced this. Let's go back to let's revisit this equation over here. So take h as usual, vanishing here. And we have expectation of trace of h of xn, sum nu k of h divided by nk, upper bounded by this. Okay. But now we know that all of these supports are contained in this interval. So if we take h like this, all of it here is just going to vanish. And the gain now is that here now we have a much stronger decay, not only 1 over n squared, which we had before, but arbitrary m. So let's do this thing of, in order to count outliers, right, we need the unnormalized trace, which means that we multiply by dn. So here I'm multiplying by d on both sides, and by n. And this is true for any m. Okay. So now this starts becoming relevant. How exactly this depends on h. But so there's some struggling between the terms. But ultimately we get that these two norms over here are O of 1, little o of 1 in probability, meaning this difference goes to 0. Whenever these matrix coefficients grows lower than exponential in n. Okay? So there was some open question of PCA about keeping strong convergence when one tensors with elements in a sub-exponential operator space. And this is something that, for example, can be deduced by hitting the whole sub-exponential regime with this C. And in particular, this implies this Peterson-Thom model. But moreover, we can get from here strong convergence for tuples of matrices of this form. GUE tensor minus k, and then let k go from 0 to L. Right, so in Peterson-Thom, L is equal to 2, but here L we can take to be really, really large. And then from this, we can use as building blocks to prove the gamma independence thing. Okay.